going to, that's what we'll do. Anyhow, welcome, lecture 3. So it's the second week of the semester. We had a homework. We're going to go over some of those problems. I got a few questions by email, but before we sort of go over those questions, we want to remind everybody of what we're doing, why we're doing it, and actually while we do that, I'm going to pull up a copy of the homework assignment. What, is Canvas not going to work now? What a time to be alive. Oh, there it is. So bear with me 1 second and we will begin. So the homework is due tonight at like 11:59. So I think some people have submitted it. No, no one has yet. Good. That means there's nothing from each grade yet. No, I'm just kidding. Yeah, question.
I did.
Did you? Yeah. Because it doesn't say, it says 0 of 9. Oh, there's been 9 submissions. There you go. That makes sense. I read that incorrectly. Thank you for pointing that out. Dude, the internet is running very slow right now. I can't even download a PDF. What a time to be alive. Okay, so what have we been doing? Well, so last class, we started our journey with propositional logic. And the reason for this is this is the basis of not just mathematical proof, but also the essence of how we design algorithms and for that sake, computer programs. It's logic. True or false, 0, 1, yes or no, heads or tails. These are all things that we can think about as being similar. And really, when it comes to computers, if you want to think of it from the most concrete sort of scenario, when you press a keypad or you do anything, what it's doing is it's measuring current on or off. And then different currents have different signals of what we call bits. These are zeros and ones, and that tells what to display or what to compute. So anyhow, you guys, you know, that's not the purpose of this class to understand all that, but some of you know that stuff. And if those of you who do understand how all that works, I want you to think about that connection with what we're doing now. And on the flip side, we also want to have rigorously sound mathematical arguments. And that's why we do this. Okay, so what we talked about last class is we basically covered, so we covered material in section 1.1 of the text. And a little bit of what we talk about in 1.2. Now 1.2 is more or less, you could think of it as applications to what we're starting with. So again, we're not going to go super deep into that, but you should read that for your own sort of personal, you know, if you're curious about that stuff. Does that make any sense? So most importantly, what you should be able to do after homework or after what we did in Monday is you should be able to answer these questions on homework 1. And really section 1.3 is an extension of 1.1 and 1.2. It's really, you know, we're slowly building things that could have all really been squished into one place, if that makes any sense. So what I'd like to do is I would like to take this time to answer any homework questions that someone might have. Does anybody have a question about, we could start with number 1. And by the way, if you have a question, let me know. Anybody in here? Yeah, we'll start here and then we'll ask the online community. Mackenzie, which one? Number one, all of them?
No, not number
Which one? 2F. So the first question is 2F. All right, so we want to express these things become, ones like F become quite complicated. And what we need to do is we need to, I alluded to this at the end of the last class on Thursday. You have to think of like this order of operations that we're dealing with, okay? And what I said is one way to avoid ambiguity, is to use grouping symbols and work our way from sort of the inside out. Does that make any sense? I'm gonna bear with me one second. I'm gonna shut this. Anybody getting a free education? Although we're online, you could be sending this anywhere. Okay, so, if we just to build up as a little bit of warm up, let's, instead of we jumping right to F, let's look at a couple of the earlier ones. So we sort of, we don't want to lift the heavy thing first. We'll start with sort of the baby stuff, if you will. So what does the problem say? The problem says we have two propositions. So P is equal to, or not equal, that's sort of a weird way of saying it. So a lot of textbooks use a colon. But I guess you could, if you wanted, put an equal sign. So P is a sentence. And this sentence is the temperature is below freezing. And then Q is the proposition, it is snowing. So let's first remember that these are in fact propositions. And the reason they are propositions is they can be verified true or false. It's either snowing or not, right? Now you might say, well, what does it mean? Well, if we need to add context, well, context, but under this context, it can either be snowing or not. And it can either be above or below freezing. How do we know that? We take a thermometer and measure. Right? We can answer that either yes or no. Okay, so let's just list some of the basic properties. So not P, this means not P, you would say the temperature is above freezing. That's one way of saying it. But of course, you could also say the temperature is not below freezing. So I mentioned this as well. It's important that you guys understand that the English language, we can sort of use it to our benefit. There's multiple sentences in the English language that mean the same thing. One of the examples most of you who've had me before have heard me say all the time, Fink is younger than O'Grady. O'Grady is older than Fink. That is a fact. It's a true fact. It's a proposition, actually. But there's two ways to state the same proposition. Does that make sense? Okay. And then we wanted, for full clarity, what if we said not Q? We might say it is not snowing. So to sort of build up to, let's do, I don't want to do all of them. Let's do P implies Q. Well, one way of saying this is if it is below freezing, then it is snowing. I mean, we're just translating. Remember, we're translating a mathematical statement. Symbol implies symbol. We're translating that into the English language. So one of the skills, as I said last week, is you want to be able to do both. You want to be able to translate from English to symbols. You want to be able to translate from symbols to English. That's what we're asking you to do on this homework. Okay, now let's get to the big boy fun. The big fun is F. So Actually, let's do one more. We'll build to it. So let's look at P and Q. What is P and Q? Well, this means the temperature is below freezing and it is snowing. Now, again, what I really need you to note is this is in fact a proposition because it can be verified, whether it's true or false. So for this statement to be true, both would have to be true, or both would have to be false, right? Anybody have a question about this? All right, so that's one point. Let's now jump up a little bit in fun, and we'll do F. Before I do that, though, does anybody have a question or comment? Is there anybody sitting in the waiting room, or did we get everybody? Good? Oh, no, now we have someone in the waiting room. Imagine that. As soon as you say, they pop up. Here they come. Oh, excuse me. All right, so very good. Let's do F. I just lost it. Okay, so for F, now we want to do, I'll use the one we've been using. We'll get there, Josh. Patience, patience. So now we want to do this crazy one. So let's think about the English words that we can associate with these mathematical symbols. So what I mean is that thing in front of P, I associate the word not. Not, I mean, I don't have to always say not, just like I did earlier, but I associate that word. And the English word I associate with the middle thing, that disjunction, that is the English word or. And then the conjunction between P and Q, I usually associate that with the English word and. That's how I would encourage you to think about it. Okay, so how would I think about this? And it might sound funny. And here's the thing you have to remember. It's okay to write it out in a direct translation and then say, okay, this sounds weird. Maybe there's a better way of rewording it. Does that make sense? Right? I mean, that's a common thing we do all the time, particularly if we're translating from one language to another language, right? We might say, okay, well, this guy is, this sounds funny. Let me try to use another word or another phrase to make sense of it. Are we cool with that? All right, so what if we just go directly with what it says? So if we just replace those symbols with the words, let's see what we get. We get this. We get, it is, I'll just use not right now. So it is not below freezing. Or it is below freezing and it is snowing. Now, this seems like a completely ridiculous sentence, but it is a sentence. And it can be verified to be true or false. So what you need to say, I mean, this is completely valid here. There's nothing wrong with what we wrote from the translation sense. The question is, does it seem like it makes any sense, not even mathematically, but just in, it almost seems like it's just words, right? It doesn't seem like it makes any sense, but that's okay.
And like, what do the parentheses?
That just means we operate on that first. That will become more clear. Okay, so that's a good question. You don't like put parentheses around English sentences that say, you know, right. So what we're thinking about is from a truth standpoint. So what would you, so the question that Mackenzie asked, she says, what do the parentheses mean? Well, right, but that's the most important part, because what we're going to do if we want to validate the truth or the falseness of this statement is we start with what's in the parentheses. We first say, okay, P and Q, what is the truth value here? And then once we have that, we've reduced in our problem, instead of having three things that are, or two things that are connecting it, we're now down to just one. So you start with the and then you reduce to the or. Does that make any sense? And it's more, it becomes a little more clear when you start thinking about, play around with these sentences for a while. Think about how, maybe write a truth table out for this statement and see, okay, I always use that example last class, is when am I lying to you? When do I make a promise that I don't keep? Right? Or stuff like that. And again, a lot of this stuff, you have to remember, learning it is not an instant thing. It's not I see O'Grady wrote that down, that makes sense. That's not how most humans learn this stuff. Most of us learn it by struggling to figure it out, having someone show us something, and then us pondering more about it. It's more of a process than it is an instant moment. I don't know if that makes any sense to you, but that's mathematics in a nutshell. It's a process. And oftentimes what's unfortunate is when we're teaching like in a vacuum like this, you guys don't think of it as a process. You just think that it must have came to someone instantly. And this propositional logic was hundreds, if not thousands of years of human endeavor to finally make sense of this a couple hundred years ago. This is not like, this stuff is, don't forget, we're asking you to learn things that took us as citizens of the world a long time to come together and develop. So, you can't expect that, oh, I'll read the book once or I'll attend a couple lectures and all of a sudden it makes sense to me. But that is a good question, though, Mackenzie, is how do the parentheses translate into the sentence, right? And so perhaps to make it more clear, we could reword this sentence so that aspect comes first. Does that make any, I mean, again, I always say, does that make sense? And you guys are usually like, no, O'Grady, it doesn't. And I'm like, rats. Any questions? So the last thing I'll say about 2F is you bring up a great point, this ambiguity. And that's something we're going to have to reason with and dive into when it occurs later on. Another way of thinking about it is the truth value of this sentence might actually be redundant in a way that we're making a sentence. I don't know this to be sure, but like, I'll give it a better example. Like, I think from a mathematical standpoint, we talked about this idea of there's a hypothesis and a conclusion. Well, sometimes a hypothesis might be redundant. The conclusion might hold anyhow. Does that make any sense? So on one hand, we might have a very wordy and complicated statement that's unnecessary. And we'll see that from time to time. An example that you might be familiar with, I don't need to say that a function is continuous and differentiable. That's redundant because we know that if you are differentiable, you're automatically continuous. So I could say the function's differentiable, and that includes the continuity aspect of it. So it would be redundant for me to say continuous and differentiable. Does that make sense? So again, we'll dive into this stuff more. All right, Josh asked about 6. Before we get there, does anybody want to ask about 3, 4, or 5? Because 6 actually is what we were going to talk about today. De Morgan's laws. Man, you've made it in this world if someone names something after you. I think one day we'll all have the O'Grady laws or the Holy laws or the Mackenzie Laugh laws. Yes?
I was confused a little bit about
5. All right, let's see. Someone chat it up. Zoom. Yeah, Carly, Zoom was down. Yep. Yep, Michelle, we'll get there. All right. Ooh, I'm not getting mean. I'm like, Josh, patience. Michelle, we'll get there. That's mean. I yelled at Fink when he walked in. I said, yes, Fink, we'll figure it out after class. I kid, of course. See, I'm laughing. Ha. Love you guys platonically. All right. So I keep hitting the wrong mouse. This is confusing having multiple screens up. You said, what number did you say, Mackenzie? 5. Oh, okay, great. So let's actually, let's pause from, let's pause for a second to sort of, I mean, to be fair, 5, 6, 7, and 8, we really didn't give you the necessary, we didn't give you the necessary information to complete them yet. Does that make any sense? So let's look at this stuff. So to complete homework number 1, we need some new ideas. So the first thing we have to do is we need to make sort of some definitions. Now, I alluded to this, and I think we actually said this at the end of class, but it's worth repeating again. So we say 2 propositions. So these are possibly compound. That means it can be made up of many pieces, like we talked about. I guess I should learn how to spell compound. It's a U. So we say they're logically equivalent. When are they logically equivalent? When do they mean the same thing? So before I finish this, let's think about this. I used this example prior because it makes sense in English and in our intuition of language. O'Grady is older than Fink. That is a true statement, right? I'm 40. How old are you, Fink? 19. Holy. So that is a true statement. That's a proposition. It happens to be true. Another proposition that happens to be true is Fink is younger than O'Grady. Another sentence that says the same fact is my sentence the other way. So we say those things are logically equivalent because they mean they state the same fact. 2 ways to say the same fact. So we say that the 2 propositions possibly compound. That means they can look like what we just talked about. They can have all kinds of conjunctions and disjunctions and stuff like that. So we say they're logically equivalent if they have the same truth value all the time. So another way of saying it is they have the same truth table. And then there's another word that's useful, and this will help you with number 8, that we often use, is if. A proposition, once again, possibly compound. Well, I guess I shouldn't even say that. It doesn't make any sense the other way. So talk about redundancy, O'Grady. So let's state it. Okay, let's put it this way. If a compound proposition is always true, we call it a tautology. So that's the other word you need to know. So let's put this in symbols. Before I do that, does anybody have a question then? Okay, so in symbols, we can say these things. Excuse me, the following way. So that means P if and only if Q is a tautology. So in this case, we sometimes write P with 3 bars. Not an equal sign, we usually call that an equivalent sign. Notice I say in this case we sometimes write. Not everybody uses notation. I believe your book does that. So does anybody have a question about this? I know we hate definitions, but they're important. All right, so let's do a famous and important example. I'm going to drive myself nuts. I keep hitting. Every time I go to do this, I hit the mouse for the other computer, which you don't see. All right, so let's do that. De Morgan's laws. De Morgan. So what are De Morgan's laws? De Morgan's laws is there's 2 of them. They are a way to, I like to think of them as sort of this goes sort of to what we talked about with your original question, Mackenzie, with the parentheses. How do we operate with parentheses and negation? So what they do is they tell us how we can do it. So in some ways, they're kind of like a distributive law. Do you remember how you combine addition and multiplication? That the Morgan's laws, they're not, it's not, I wouldn't think of it like as a distributive law, but it's in the same flavor. How do we interact? How does the negation of the disjunction and the conjunction of something behave? So let's just state them. The first one is negate P and Q. What is that equal to? Well, it turns out that it's equivalent to this compound proposition has the same truth value all the time as not P or not Q. And then the other one is, what if we negate the disjunction? What if we negate the or statement? Well, symmetric intuition comes to play, and we get this. So let's put this in a nice, pretty box. So here's what I would tell you. You need to know this and how to verify. That is extremely important. And so on the homework, I asked you to do that on problem 6. So we just did number 6. We asked you to write them down, here they are. You probably could have copied them off the book or off of the internet. By the way, De Morgan's laws also apply to what we call set theory, which is something we'll get into later. So if you Google De Morgan's laws, which maybe you did, you may have seen it written differently. This is propositional logic, but there's a version of this that is in what we call set theory, the theory of collections of things. All right, so we're going to do problem 7, and then we'll go back to 5. How's that sound? So actually, you know what? We'll do 5 first, because 5's a little easier. There's not as much happening, so we'll do 5 first. So let's go back. So these are problems 6 and 7 on the homework. So, okay, so let's look at let's do number 5 before we do that. So the statement of the problem says, use a truth table to verify the commutative law. You know, that is what you expect. The order of saying two things that are true shouldn't matter, right? I can say O'Grady is 40 and this room is not full. That's a true statement, right? And then if I reverse it, if I say this room is not full and O'Grady is 40, that is also a true statement. So just like with, you know, this is a sort of the version of propositions that would be similar to the commutative law with 4 plus 5 is the same as 5 plus 4. Do we get that? All right, so, okay. Good. So how do we do this, though? What's the way of doing this? Well, the first thing you do, and we said this on Thursday when we did some of these, is you have to make a table. So let me get out the straight line. I'll take a square. So here's how I'm going to do it. I'm going to say, okay, what kind of table am I setting up? Well, I have 2 statements, P and Q, 2 propositions. And then I am going to create a compound one using the disjunction, or. So let's actually save that fun for you, and we'll do the and, which is almost the same thing. Right? That makes sense? So what I'm going to do is, I know all the time, the first thing I have to do is I have to write all the pieces. What pieces do I have? Well, I have a P, and I have a Q. And then the only other piece I have is I need to study P. Well, I guess, you know what, let me erase this. Here's probably a better way of doing it. So let's look at all the things we want to study. We have P and Q, and then we want to look at P or Q. We'll just do number 5. What the heck? You can do the other one for fun. And then we want to look at Q or P. So there's 4 things we want to look at. So let me put a box around this, because my job is to show that the columns over here are in fact the same. So I need to show that these 2 guys are the same. Does everybody understand what I mean by this? My job is to show that this, oops, I need to show that this and this have the same truth table. So what I'm going to do is I have to write that, since I only have 2 building blocks, I have 2 pieces, P and Q. What are all the scenarios I have? I have 4 scenarios. We know that they can both be true, true, false, false, true, or both be false. Right? So let's illustrate that. We have a true. We can have a true and a false. We can have a false and a true, and then we can have a false and a false. That is the only scenario. Or excuse me, that's all the scenarios. There's 4 scenarios. Now, suppose I had another guy in there. Maybe I had P, Q, and R. Well, then I would no longer have 4 scenarios. I would have 8. So this is a simple counting thing. How many propositions do you have? If you have 10 of them, you have 2 to the power 10 scenarios. If you have 6 of them, you have 2 to the power 6 scenarios. 3, 2 to the power 3, which is 8. You can list them all out. Those are some big numbers. 2 to the power 10, 2 to the power 6. What's 2 to the power 6? 64, right? I wouldn't give you anything like that. But you should be able to work with 3 of them, P, Qs, and Rs or something. It's just your table becomes bigger. Okay, so here we go. We need to now remember what statements. What is P and Q? Well, this is almost a simple and redundant exercise in the sense that, okay, when is or true? Now, you might have to go back in your notes or read in the book, but when is or true? Well, what do you mean everyone? But it's going to be clearly true if both are true. And then it's going to be true if one's true and one's false, because I'm not breaking a lie. I'm not lying or breaking a promise. And it's going to be true here. And the only time it's false is here. Well, then the same thing happens here. If we just use the definition of or, we get the same thing. I mean, this is all there is to verifying it. It almost seems like it was redundant, right? But it's in fact not redundant. Yeah. Well, it's okay that things aren't actually, you know, some things don't require anything other than you writing down the definition. That's all you're doing. All you're doing is writing down the definition for this guy and then writing down the definition for this guy. And you can, when you're thinking of the definitions of conjunctions and disjunctions, don't think of it in words. Think of it in truth tables. That would be a piece of advice. Think of for these definitions of like and or, think in terms of truth tables. Now, of course, Mackenzie, what you did is not wrong. You said everything's true but the last one. That's another way you can remember or. And then and is the opposite. Everything is false except true, true. So there's certain ways you can sort of train your brain. I need to get a sip of water. Man, talk about cotton mouth. Whew. There's a certain way you can train your brain, I think, to know these things, but I think the best thing to do is just to have the mental image of the truth table in your head at all times. That's sort of O'Grady's advice. All right. So let's get to De Morgan's laws. I'll do one of them. You can do the other one. How's that sound? Okay. So let's now verify one of De Morgan's joints. Let's pick one. Well, let's just pick the and. We did or last one, so we'll pick this one. Okay, so there's a lot of ways you can go about this. Everybody has their different strategy. You might go on Khan Academy and watch some other, person give their strategy. Maybe you read the book, you see their strategy. Maybe your cousin Lily or Billy or whoever took a class like this and can help you. I don't know. Everybody has their strategy. I am trying to teach you in the way that I learned it for myself, right? And I'm not going to lie to you. You're going to struggle with this stuff at first. It's weird. It's a different way of thinking we're not used to doing, and so it's kind of sort of difficult. So what I'd like to do is I like to look at all the pieces in here. I don't like to skip steps. I like to literally pick every single building block of this thing. So once again, what am I starting with? I am starting with P. I am starting with Q. I have there's two propositions involved in this. And then I want to study a compound proposition that's made of them. So what pieces do I need? Well, the first thing I need on the left-hand side, I recognize I need a P and Q. I know I need that, right? On the right, and then on the left-hand side, I need to negate that as well. So notice I'm going one piece at a time. Now on the right-hand side, what do I need? I need not P, I need not Q, and then I need the combination of them in terms of OR. So in my mind, I have 1, 2, 3, 4, 5, 6, 7 things that I have to build up to. Now, there's only 2 of them that I want to compare, but it's going to take me, the way I've set this up, it's going to take 7 things. So let me build my little block, make it a nice little table. The way we like, let's use different color. We'll use pink. And then let's make sure we divide these up properly. These 2 are our starting points, our building blocks. Then these guys are pieces to the puzzle. Now, what I'm going to do is I'm going to make sure I don't forget which are the 2 guys I'm most concerned about. So I am going to put a green sort of star here, because this is the guy I need. This is the left-hand side of my equation, and this is the right-hand side of my equation. Now, in order for me to verify this De Morgan law, I need these 2 columns that I have starred, I need them to have the same exact truth value. So once again, we start the fun. I know that I have 4 scenarios. I have a true, I have true, false, then I have false, true. Then my last scenario is if both statements are false. So this is how I do it. I don't know, other people might have a different way of doing it. Some people like to be cute and make their tables as small as possible. I'm the opposite. I like to go slow and deliberate. All right, so as we said earlier, P and Q. Only time it's true is when both are true. So the definition of and, and I have it in my head, the truth table tells me this is true, false, false, and then what? What's the truth table for and? Oh, I'm asking you. This is where people get confused. Now, you said, and I'm not trying to pick on you, Mackenzie, but you said it out loud earlier, so I said I have to sort of, I have to tell her that this is how we're going to do it. It's always false, right? The only time and is true is when both are true. Okay, so now we want to negate this now. We want to take this column that I just wrote and negate it, because that's what the next column is. So you just switch, it's opposite, on, off. So then we automatically know by the definition of negation that's F, T, T, T. So I got my 1 column. Now, common error for amateurs like yourselves is to think, okay, now I'll just make the right-hand side look like this. That ain't what you want to do. You want to verify it slowly and steadily. Okay, so now let's go very, very, very carefully. Now we're going to do not P. What's not P? Well, that has to be the opposite of all what P is. So if P is true, not P is false. So that means I readily get this table, FFTT. So I'm just negating the very first column. Now I'm going to negate the second column because that's not Q, F, T, F, T. So once again, I'm negating the second column. Are we entertained yet? Are we having fun? I'll tell you what, if someone asks me how much fun I have, and I say like on a scale of 1 to 10, I'm having 9.9, times 10 to the 347. That's a big ass number. All right, so finally now I have this column. I have the 5th and 6th columns. I need to use the truth table for or now. Or. And so just like I think, Mackenzie, you said it, I could pick on you again, but everything's true except the last one, right? But be careful, because that's only when it's the original true, false. We have to be very careful. So now, using the truth table could give us the wrong answer now. So what you need to do is you need to look at this, because this one is actually flipped now. So we know for or, if both are false, it's false. So actually we get false, and then we know if at least one is true, it's true. So we know, bingo. Whew. And just as we had hoped, look at the starred columns. They are the same. We are done. We verified De Morgan's law. One of them, at least. Now the other one, which you can do for yourself, is almost identical. It really is. Whew. What a time to be alive. Isn't this fun? Okay, so let's make sure we're clear. So on how we make this, we conclude this, we would say, since the starred, is that a correct way? Is that starred? Is that how you say it? So since the starred columns have the same truth values, we have proven, or I shouldn't say proven, that's kind of a, we didn't invent or describe that yet, but what we have done is we've proven the propositions are logically equivalent. So if you want to one last time write it in symbols, we could. What were the symbols? We proved that, oh, why did I lose things? What's happening? Uh-oh, is Zoom about to crash on us? No, okay, good. So we proved not P and Q is logically equivalent to not P or not Q. Woo! Is that fun?
A question, sir.
Yes.
So I'm sorry if I missed this, but for number 7, are there any specific amount of tables you want me to write?
No, what do you mean? I mean, you could do it all in one table if you'd like. So the question was, for problem 7, is there a specific amount of tables? No, I mean, again, if you wrote smaller, if we go back to this page, if you wrote smaller, you could have killed both De Morgan's laws with one table. Does that make sense? You could have just made more columns and then showed that 2 match and 2 others match. Or okay, you could have done a bunch of tables and then took the results of each of the smaller tables to get the total result. There's more than one way of doing this. Now, there's also lots of incorrect ways of doing this, but there's more than one correct way to reason this. Does that make sense? So what I'm saying is I could have first used the first 3 columns and then gotten a table, and then used that information to get a truth table for the first starred column. And then I could have done another table to get the other side. Does that make sense? Does that answer your question?
Yes.
Yeah. So yeah, I mean, most people would either write it all as one, like, and they would do one like this and then another one for the other statement. So 2 that would look like this. Does that make sense? I don't know if I'm being clear.
Thank you.
Okay, so very good. That's problem 7. You should know those. You should know how to verify them. All right, good. So let's look at problem 8 now. And I think a lot of the people clamoring for help with this one, which is a fair amount of you, you're going to kick yourself when you're like, oh my God, this one was so easy, right? So for number 8, we need, or let's not even say we need, let's say what we're asked to do. We are asked to show that P and Q implies implies P is a tautology. So to do this, we must show it's always true. So one way to do this is a truth table. So let's make a truth table. And once again, let's think about how I'm going to build it. So I start with a P and a Q, and then I want to look at P and Q, and then lastly, I need to look at P and Q implies P. So this is what I want to look at. Okay, so let's do that. We'll use different colors here because why not? So what are our 4 scenarios? We have 2 propositions, P and Q, which means we have 4 scenarios. Count them. 1, 2, 3, 4. So we have true, 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 false, false, true, and then false, false. So the only time and is true is when both are true. The rest is false. Okay, so now I have to go to my definition of the conditional, the implies thing. When is that going to be true? And when is that going to be false? Now, this is a little subtle. So I need to, right now, I need to look at the 3rd column and the 1st column. Those are the things that matter. And the problem is it's reversed, sort of, like, because we're reading instead of left to right, we're going to have to read right to left. We're going to have to read the 3rd column and compare it with the 1st column. So what you need to remember is when is the conditional true and when is it false? Okay, so what do we know about the conditional? We know that it's true sometimes, and well, right, okay, so yeah, but they are all true. They should be, but we got to see why, right? So you're correct in that they better be true, but we can't just write true because we're told. We have to reason why. If you just copy it down that they're all true because you know that's the point of the problem, you're not learning anything. You're just, you're like a poor excuse for, you're like a monkey at the zoo. You just mimic. We want you to reason here. Part of doing this helps you reason logically. So when is when is the implication if then true? When is it false? Now it's okay. You can look it up. You can just go Google truth table if you want. I'll bet you truth table for implication or conditional, whatever word you want to use. So the only time that P implies Q, or I shouldn't say that here. Something implies something else is false. It's only false one time. When is it false? It's only false when you are lied to. If I make a promise and break it. So the only time it's false is if your hypothesis is true, but your conclusion is false. So when is P and Q true? Okay, P and Q is true here. True implies true is also true. And then the other times it's true. It's always true every other time. So it doesn't matter. False implies true is true. False implies false is true. And of course, the other time we have false implies false again is true. So let me explain this. This is important because I don't know if you guys are understanding what I mean. And so a good way to sort of think about this is note, what am I using? So I'm going to use different variables. I'm using this. It might be helpful for you to do this. I'm using, let's say, R in S now. And then let's say R implies S. So for implications, this is, say, true, 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 false, false, true, false, false. Now, the definition of this says it's false only once, in this case, where you're lied to. I make a promise, I don't keep it. Every other time, I'm not lying to you, so it's always true. So if you're keeping score at home, I'm thinking of this as R. When I read this table, this is my R, and this is my S. But that second condition never happens. It doesn't happen. I never have true implies false. I don't have it. There's nowhere in that third column where you have true, and then in the corresponding first column you get false. So this might take some time for you to sort of come to terms with it. And again, you shouldn't get discouraged that it's hard for you. That's called learning. It's called, persevering. But you do need to ponder this kind of stuff. Does anybody have a question about this? And again, don't forget, we're going to be applying this reasoning to mathematical arguments. That's the main thing we're going to be doing in this class. You're going to be using these ideas to prove things. Not just compute things, but prove things. I might say to you, show that any number that looks like this is divisible by 3. Remember when you guys were kids in school, you might have learned tricks for factoring numbers. Obviously, if it's even, it's divisible by 2. If the numbers add up to something, it can be divisible. We talked about that in some of your other those classes. That we never show you why, though. Why is that true? Just because your third grade teacher tells you it's true, does that mean it's true? Just because it works on all the times you try, it verifies? That doesn't. There's lots of things that have patterns that work and the pattern fails somewhere. We'll show you examples of that here. So a mathematical proof isn't, hey, look at the picture, it works here. No, that's not how it works. So we need these sort of ideas. And again, I can't emphasize this enough. If you actually paid attention when you were in a class like calculus and you thought about how these things that we stated were always, if this is something, then that. If the function is continuous, then it's integrable. If this is true, then all these things are true. Really important things like if x is in the radius of convergence, then the series converges to the function. Things like Taylor series. You guys, you don't appreciate that when you're sitting in a class, but in the real world, that matters. Making sure the hypothesis is met so that the conclusion is guaranteed, that being theoretically sound is really, really important. If we didn't know that it's theoretically sound, then a computer could just go forever looking for something that just doesn't exist. So, when you get, I'm sort of getting a little off topic, but that's how I roll, right? We could just talk about other things. You want to talk about my weekend? It was great. How was everybody's weekend? Good? That's good. But no, I am off topic, but I'm not, because there's so much to this process that you guys have to understand. Learning is a process. And we're not just asking you to learn things like memorize something. We're asking you to learn hard things. This is difficult to learn. So you can't get discouraged or say I'm stupid, even though you shouldn't say stupid. My 5-year-old told me, don't say stupid, Daddy. That's not. But you can't think you're stupid. You gotta accept the fact that it's hard, and every one of us can learn this. It's just for some of us it takes longer than it does for others. Just like some of you are stronger than others, and some of you can run more distance quicker than others. That's just the way life is. Unfortunate, some of you are more susceptible to viruses than others, right? I mean, that's what it is. That's life. Our brains are all different. Our body's made up differently. You know, some of us learn this, but there's very few people on the planet that just get this stuff. And even if you work with tutors or other people and discuss it, usually if people seem to just get it, that's because they already seen it. Okay, very good. Any questions about this homework before we move on in the remaining minutes? I mean, we kind of did them all, right? And by the way, for those of you who joined a little late, all you'll see right now on Canvas is the first homework. I got to add the lectures too. I forgot to upload that. Okay, and then we'll put those quizzes on, and you'll have a few days to do them and stuff like that. I don't know why I'm calling them quizzes. That's anything that could come to my head. All right, so and what remains, we gotta sort of set the stage for what's going to happen next. So it's not a bad thing for you to work and continue to do things. So here's my advice with this kind of stuff. I keep grabbing that stupid mouse. I'm going to lose my mind. So here's O'Grady's advice. Open the book or scroll in the PDF and do as much of section 1.3 as you can. What I mean by that is, I mean the problems in the back of the book. Do the odd ones. The solutions are in the back of the book, by the way. And I mean, what's that? Someone saying something? Oh. Do it and do the examples. Do them on your own, the ones that they work out in the book. Just practice. I'm telling you, you will benefit from thinking this way. I'm not lying to you. Okay. Sweet. So here we go. So we got to set the stage now for what's important, what's next. So what good is all this stuff doing? We just did some problems with some symbols, and right now it could be completely meaningless. How do we turn it into useful for mathematics? How do we turn it to be useful for constructing algorithms, programming a computer? You know, so what is happening? Someone mute. Whoever's making ruckus, mute, please. How do I mute you? I'm just kidding. I mute you all now. Silence. Okay, so what's next? So we need so what we need to do is we need to connect to math. So what I mean by that is, how do we handle I'm going to call these things. How do we handle things such as 3 plus x equals 10? Well, we know that it's going to be true some scenarios, it will be false in others. So how do we sort of quantify or put context around when it's true, when it's false? Right now, that is not a proposition. However, as I said before, if we add context to it, it becomes a proposition. So again, I repeat this because you can't verify true or false right now. We need to sort of develop a way so that we can. So hopefully you guys understand that sort of dilemma. So we know it can be true at least one time. So how do we make sense of that? Well, so it's useful to note that truth depends on the value of x. So this means the truth of the proposition, or let's not say the proposition, let's be more general. So this means the truth of certain propositions can depend on variables, right? So for this reason, it's useful to use notation such as P of x is, what was the original thing? Was it x plus 3 equals 10? 3 plus x equals 10. So if we do that, then what is P, not 4? What is, say, P of 1? P of 1 is false. But say P of 7, which is 3 plus 7 equals 10, is true. Does this make sense? So in this case, we call P of x a propositional function. So it's not just a proposition, it's a propositional function because it depends on something. So, and then we call the equal sign the predicate. Why do we call it the predicate? That's because the truth depends on, this is what's causing the truth to depend on something. Does that make any sense? Does anybody have a question about this? Let's do some examples and then let's use Q. So let's do Q, X, comma, Y, comma, Z. Now we'll have three things that might depend on it. So watch how I'm careful with my language here. So let this be the statement or the sentence. Say, X plus Y equals 3 plus Z. Note, when I put numbers in, notice the words I'm using here. Proposition, say Q, 1, 2, 0 is true. If you plug 1 in for X, 2 in for Y, and 0 for Z, you get a true statement. Verify that for yourself. However, Q of 1, 1, 1 is false. And we could give other examples. You can think of different solutions, and then those would be trues. And if ones that don't make it a solution or a true statement, it'd be false. Now, right now we're just practicing saying something's true or false by plugging different numbers in. But what we want to do is we want to build to it's a little more useful where we could say something like this statement is true when the variables meet certain criteria, for example, right? So we want to build a language that allows us to be more specific, not just give you a random example here or there. Does that make sense? So we'll do more of that on Wednesday. That's okay, Sean. Any questions before we leave? We're supposed to leave by 12:15, so I don't mean to rush out, but does anybody have a question? I'd be happy to answer it. Comments? Concerns? All right, gang, stay tuned to Canvas, and I will see you guys Wednesday. Thank you very much, and have a good day.